Okay. Okay. No, I'm very happy to be again in Warsaw, and this time I'm going to speak in English because last time somebody found the YouTube video of my previous talk in Warsaw, and they said I could not understand anything of category theory. But that was because it was in Polish and it was the English speakers. So yeah, so this time it's in English, so you should be able to. It will be really easy, right? Okay, so this talk will be. I mean, I usually use a whiteboard and draw lots of diagrams. This time I decided I'm going to actually write some code in Haskell. Okay, so most of the stuff, it will be about category theory, but it will be in code. Okay, so it will be presumably easier to understand. Although, I don't know, the diagrams are nice, right? So I want to talk about arrows, the arrow library. And they are a very interesting thing from the point of view of category theory. Because they expose a lot of interesting structures in category theory. They expose things like category itself, right? But also a monoid and a monoidal category. So this is like, and the same thing is seen from different perspectives. Like we'll be talking about pro functors as first of all, mappings between categories, but then also as arrows inside a category, and then as objects in a category. So we'll be like really juggling these ideas. So you have to like constantly switch your mind from one view to another view and to yet another view. Okay? So let me start with well, definition of category, right? So a category is just a bunch of objects and morphisms between them, these arrows, right? I usually draw objects as little piggies and they throw little arrows at each other. But this time, this will be serious talk, okay? So there will be code. So, starting with an import, okay? So this import actually is for the purpose of hiding stuff rather than exposing, right? So these things like ID and dot, right? They're defined in the base, and you don't have to include anything. So if you want to redefine them, you have to hide them, okay? And this is a way of hiding this. So a category is defined in Haskell, at least. You know, the objects are just types. So that's easy to understand, right? And normally, arrows or morphisms, okay, I'm going to use the word arrow sometimes as for morphism, but we are talking about the arrow library, but that's a different thing, okay? Morphisms are just functions, right? And the important thing that you do in a category is that you can compose arrows or morphisms, right? So this dot, this dot is just like the simplest symbol that you can think in a language, right? Just a single dot. In Haskell means composing functions, right? So function composition. So you compose arrows, right? But you have one object on one end of the arrow and another object on the other end of the arrow. And then from this object, you have another arrow. You compose them, and you get a third arrow that goes, right? So that's like a standard thing, right? But it's category theory, really, right? But we know this stuff, right? And there are several things, just a few things that define a category. One is the composition of these morphisms. The other is the composition has to be associative, right? So that like if you compose first these two and then the third one, it's the same as, you know. So this is something that we know that works for functions. No problem. Then there has to be an identity arrow. For every object, there has to be an arrow that goes back on this object, and it's an identity with respect to composition, right? So this identity is an identity function. Now, in category theory, you have one identity morphism per every object, right? In Haskell, it's just one function, right? But really, this is a polymorphic function. So this is really a huge family of functions. Like for every type, there is an identity for this type. But it's just the same formula. So it's like we think of this as one identity function. But this really is like an identity function for every single type, right? A polymorphic function is defined for every single type. So that's it. That's the category. So since we have hidden these two guys, we can redefine them, okay? And we can define the category class, and it's defined in the library. So when we define a category, we define objects and we define arrows. When we do this in Haskell, the assumption is that the objects are types, okay? So the only thing that you have to define is arrows. You have to define morphisms, right? And these morphisms, well, a type of morphism. We have to define a type for a morphism, right? If we want to define a category that's just not the trivial built-in category, then we just define a special type for our morphisms. And this parameter cat is just describing in generic terms a type of morphism, right? And it has to fulfill the following things. There has to be one polymorphic thing from A to A, okay? So this is like a polymorphic function that goes, well, I'm saying function. Sorry, this is not a function. It doesn't have to be a function. It could be something else, something that connects two objects, right? And later we'll see things that connect objects that are not functions. For instance, profunctors, right? So it's important to like keep in mind that the simplest example of this is just a function type, right? An ID is just a special element that goes from A back to A, and it's an identity with respect to composition. And we have to have composition. So a composition is this operator dot. And this is why we were hiding this operator dot, because we want to override it for every category separately, right? So, so here I've written this in the first line in the definition of identity, right? I wrote cat in back quotes, right? So that I can use it as an infix. This is where like it's going from A to A. It's like an operator, right? So I can use it as an operator. In the second line, I was too lazy and I didn't do that. I'm just using it as a prefix, right? So cat from B to C, if I have a cat from B to C, so it's like I have a connection from B to C, and I have a connection from A to B, then this gives me a connection from A to C. That's what's composition about, right? It's kind of sort of inverted order of these things, but this is like when you compose functions, in Haskell, you invert the order. Okay. And of course, once you do this, then suddenly if you want to like compose regular functions, the compiler will say, I don't know how to compose regular functions because you have hidden the dot from the base, right? So if you do this, you probably want to do this as well. You have to like say, by the way, the thing about functions is that they also form a category, right? So the instance of the category, sorry, this should be category, not cat. Okay, instance, sorry. this here should be category, okay? So it's an instance of this class category for this operator, the arrow operator, which is just a type constructor for function type, right? It takes two arguments, which are two types, and says, okay, I'm a function from A to B, right? So in order to show that functions form a category, I have to define ID, right? Because I have hidden it here. So I have to define ID that's really equal to GHC base ID, the thing that I have hidden. Now I'm explicitly invoking it. So this is the identity function. And the dot that I'm using here, defining here, is actually the one, this dot, oh, here, this little dot here, okay? From GHC base. Why did I say, I wrote GNC, okay. I didn't do copy and paste for some reason, because I thought I can like retype it from memory. Never should do this, right? Okay, but you know what I mean, right? Okay, so we have category, okay. The second thing to know about this is monoid. Monoids are extremely important. Categories and monoids, this is like the basic building blocks of category theory, and they are the basic building blocks of all programming, really, okay? So what's a monoid? Monoid is something that has some kind of multiplication, right, and identity with respect to this multiplication. So it's sort of like a category, right? But in category, you can't really compose any two morphisms. They have to match end to end, right? It has to be from A to B, and the other has to be from B to C. You cannot match them from A to B and then from C to D, right? But in a monoid, you can multiply anything you want. You can compose anything with anything, and you always get the result, okay? So I'm going to give a non-traditional definition of monoid, okay? This is not what you find in Haskell library. It's a little bit more general. Well, not really. I mean, it's the same. It's just a different form that's easier to generalize, okay? So mu here is the multiplication. So multiplication takes a pair of elements. So M is just this type from which I'm taking elements. So the source for me, it's like a set of elements of the monoid, right? So it could be integers, for instance, right? But it could be something else, doesn't matter. So I have this source of elements, and I'm forming pairs of these elements. So M comma M is a pair of elements from M, right? And for every such pair, I assign the result of multiplication or addition or whatever I call this, right? So this is my binary operator. Binary operator takes a pair and produces something. Normally, in the standard definition, this thing is curried. So it's written as M arrow M arrow M. But I like to write it in this form, uncurried form, because this will be easier to generalize later. Okay? And the other thing that defines a monoid is this unit element, right? The identity element, the unit element, where that, like when you multiply by unit, you get back the same element, right? It's like in multiplication, it's 1. In addition, it's 0. And normally, it's also written as, you know, as an element of this set M. But I want to write this element of set M as a function, okay? This is a function that takes a unit type. A unit type has just one element. So a function from a unit type to any other type just picks one element in that type, right? So instead of picking an element, I'm saying I'm picking a function from unit to this set, to this type, right? And that specifies the element. But I like doing it this way. Why do I like doing it this way? because this kind of shows you that a monoid could be defined through some structure within your category. This structure, you maybe not immediately see this, but the fact that you can form pairs, right? It's such a trivial thing, you know, it's in every language you can form pairs, right? But forming pairs really is, tells you that you have a product in your category. That you can take two objects and you can have a product of these two objects. Another object that represents these two objects, right? We say Cartesian product, for instance. So this is a Cartesian product. But in general, maybe, you know, you can have in other categories, you can have other types of products that are more sophisticated. Who knows, right? And we'll get to a product like this, and we'll see that it's not really a Cartesian product. It's a completely different thing. But still a product in some way, right? And the other thing is that this unit type, from the point of view of category theory, this is a special case of, well, first of all, it's a special case of a terminal object, okay? So if a category has a terminal object and has a product, then we can start defining monoids for it, okay? So it's like, not in every category you can define monoids, but in a category that has products and terminal objects, you can. But this can be generalized even further and say, you know, my product doesn't have to be a categorical product. It could be something called a tensor product. And this thing that I call the terminal object, maybe it's just some special object, you know, special object that's an identity with respect to this product. And in fact, you know, this unit type is sort of like an identity with respect to taking pairs. Because if you take a pair in which first element or the second element is the unit, which only has one possible element, then such a pair is equivalent to just taking this type. It has the same number of elements, you know, it's like, and it has one-to-one correspondence. It's isomorphic to this type. So this is really a unit of this. If you think of this as a product, it's a unit for this product. So this thing very nicely generalizes to much more abstract categories. And I wanted to give an example of a monoid, right? But so first I wrote a monoid. Oh, okay, let's take integer, right, as my object, and just do addition, and then the unit element would be 0, right? But that's like too trivial, okay? So I wanted to show you that functions, actually, these are endo functions. So these functions from the same type back to the same type, they actually form a monoid, right? So here's an example. This is a type integer function that takes an integer and produces an integer. So it's an endo function, right? Goes back to integer. And these endo functions, endomorphisms, they form a monoid, right? And how do I prove this? Well, I can implement mu. Okay, so mu is supposed to take two of these guys. So it takes one integer function and another integer function, f and g. How do I multiply them? Well, I do the composition. I just compose these two functions, and I get another function. And well, guess what? The result is also a function from integer to integer, right? So this is a good multiplication, right? Does it have an identity? So identity would be just an identity function. Okay, so we sort of went full circle, right? We started with a category of functions. Now I'm saying, oh, inside this category of functions, if I pick one type, integer, then morphisms inside this, for this type, the endomorphisms for this particular type, they form a monoid. So monoid is sort of a simpler version of a category. So now I want to talk about Pro Functor, but before we get to Pro Functors, maybe let's a quick reminder what a functor is, right? So a functor, in category theory, a functor is a mapping of objects and mapping of morphisms. And in fact, the mapping of morphisms is sort of more important than the mapping of objects. At least I think so, right? So this is also maybe not a standard definition, because in the standard definition, they don't really specify the kinds, right? But you can include the kind. Kind tells you what types are involved, right? So f here is not a function because it has kind. Type goes into type. So it's a type constructor. Takes a type as an argument and produces a new type. Right? So this is what a mapping of objects in category theory translates into mapping of types in Haskell. So it's a type constructor. Right? So for instance, an example of a functor is a list of some type A, right? Could be integer, could be bool, right? So it constructs a new type list of A. Given type A constructs a type list of A, right? So this is the mapping of objects. This is a mapping of morphisms, or in this case, functions, right? So if I have a function from A to A prime, I can lift it to get a function from FA to FA prime, okay? So if F is a list, you know, so I have a function from A to A prime, I can turn it into a function on lists. It takes a list of A's and produces a list of A primes, right? And this is just mapping over all the elements of the list, mapping this function over elements of the list. And these parentheses are not really necessary because of the arrow operator has the right precedence, but it's nice to see this is more categorical view. Like you take a function and you lift it into another function, right? Now, this nicely generalizes to something called a bifunctor. A bifunctor is just a functor of two arguments, right? It's like you have a function and you have a function of two arguments. Okay, so so it takes two types, one type, another type, and produces a third type, right? But if you have a function, a functor of two arguments, or a bifunctor, then the lifting of morphisms is a little bit different, because it can lift two morphisms at the same time, okay? It's much more powerful. It takes two morphisms and lifts them. So you have one morphism from A to A prime, you have another from B to B prime, and it lifts to a morphism that goes from BAB to B. Well, this is doesn't compile, huh? Renaming on slides does not work. Okay, so B here stands for the bifunctor, and here for the type B. All right. You see that. But you see what I mean, right? So it lifts it. So this bifunctor B acts on two type arguments, A and B. And here it acts on two other arguments, A prime and B prime, right? So in category theory, this is just like nothing, trivial. Because what it means, it's just a functor from a product category, right? You can take two categories and you can take a product of these two categories, and that just has this elements, has pairs of objects, and as morphisms has pairs of morphisms. So these two morphisms are really a pair of morphisms from the product category. Fine, okay? Now the interesting part is, so bifunctors are also important. It's like an example of a bifunctor. A pair, right? A pair is functorial in the first element and in the second element. And you can take two morphisms and you can lift both of them The first will be acting on the first part of the pair, and the second will be acting on the second part of the pair. Great, right? So it is a bifunctor. Pair is a bifunctor. Either is a bifunctor. But the more interesting one is the profunctor. The profunctor is like, looks almost identical. Do you see the difference? Can you spot the difference, right? so the difference is just here. You see, here I have from A to A prime. Here I have A prime to A. Other than that, everything is the same. But it's reversed. So it consumes a morphism that's reversed, right? So, right, here it goes from A prime back to A. And there are things like these. They behave like profunctors. And the simplest example of a profunctor immediately is this little arrow thingy, right? That function type. Function type, it connects two types, A and B. And it is functorial in B, but it's not functorial in A. Well, it is functorial in A, but it's what's called contravariant. Right? Contravariance. That means that this inversion. So I can implement the die map for this profunctor arrow, right? So it takes two functions. Con goes from A prime to A. Pro, so this is a contravariant kind of argument. This is pro variant, okay? So it goes from B to B prime. Right? And f is my function that goes from A to B. So this is my guy. Now p is the arrow. So it goes between A and B. So I have a function from A to B, and I want to get a function from A prime to B prime, right? So I have to precompose it with con. Con goes from A prime to A, then f takes A to B, and pro takes B to B prime. And altogether, I get something that goes from A prime to B prime, right? So a profunctor kind of consumes stuff from one end and outputs on the other. So if you want to lift it, you know, then you have to do like the pre-composing, the translation for the input goes the other way. And the translation for the output goes in the usual way, right? So these are profunctors. No, this is not the end of my talk. Okay, this is actually, I want to define something called an end. In category theory, we have ends and we have coends, okay? So an end is something that can be defined for a profunctor. And I'll show you the definition right away, okay? And it's like really weird stuff, right? Now in category theory, the definition of an end is a little bit more complex than this, because it involves a diagram and universal construction and so on, right? But it turns out in Haskell, it translates into this simple formula. But what is it, right? This is Haskell, and yet very few people are familiar with, would understand what this means, right? It's like a weird thing. There is a for all, and the for all, you know, for all, sometimes we have, maybe when we write polymorphic functions, we use for all sometimes. Usually we skip it, right? But for all x means for every type x, all of them, there is a pxx. So if I want to construct an end, what do I have to provide? I have to provide a set of these pxx's, right? P is a profunctor, has two arguments, but they are equal here. So this is like if you think of a profunctor as like a matrix, right? These are the diagonal elements of the profunctor. for x equals y, right? So they are for the same type as input and the same type as output, right? But in order to construct this thing, I have to provide pxx for every possible x. How do I do that even, right? How do I begin? I mean, I can say, okay, let me give you one for ints, p int. Okay. What about bool? Okay, p bool. Okay, what about a list of ints? Okay, p list of ints, and so on for infinity, right? So in fact, you might think it's impossible to construct a thing like this, right? Except that we actually have examples of stuff like this. We have things called polymorphic functions, right? A polymorphic function, like the identity function, right? It's polymorphic. It's defined for every type. So there are things that are defined for every type. We usually don't put for all A there, but it's implied that an identity function is defined for all possible types, okay? So these profunctors usually have, when we implement them, they usually have some kind of shape of a polymorphic function. Or at least this is a starting point for defining a profunctor and defining an end, right? So I'll give you an example of an end, and it will be like this. Now the way to think about for all x and type, because pxx is a type, right? You give it two types, x, and it produces a type, right? So for all x, pxx means give me an element of each of these types, pxx. So it is like a product. So when you construct a product, like if you construct a product two types, right? Give me an element of the first type, give me an element of a second type, and here is a pair, right? If you create a triple, you need to pick an element from one type, second type, third type. Here you have a triple, okay, right? Here you have an infinite product. So it contains an element of every possible pxx for every possible x. Okay? And that's called an end. So an example, okay? An example. So let me define a profunctor for which I can do this. Okay? This is a profunctor. That takes two functors, f and g. Okay? So they are just parameters for this thing. And it's a profunctor in A and a profunctor in A and B in this pair. So these two types, A and B. It's profunctorial in A and B. And it's defined, this is the constructor, as a polymorphic function from FA to GB. Okay? So if you think of a functor, this is a good way of thinking. A functor is sort of like a container of something. So this is a container of A, this is a container of B. Right? So this is a function that takes a container of A's and produces a container of B's for some reason. We don't know how it does it, right? So is this a profunctor? What do you think? Is this a profunctor? Right? It is. It is a profunctor because it's covariant in B and contravariant in A. Right? So here's an instance of profunctor, right? Of course, f and g must be functors, as you can see, because I'm using fmap, okay? That's why I need this constraint, is that they are functors. Otherwise, I wouldn't be able to do this. So I have to define dimap for this. Dimap takes these two functions, and I'm just saying, function from B to A, I call it BA. And this is a function from C to D, right? And it should be able, should be able to lift these two functions. So when acting on some P, which in this case is a function from FA to GB, right? Well, not really. From FA to GC, okay? From FA to GC, because A will be transformed into B and C will be transformed into D, right? Then I can take the argument and F map, because what's my argument? My argument is FA, my argument is FA, right? So I'm F mapping over it because I want to transform A into B, okay? So if I'm F mapping BA over FA, I get something that gives me an FB, right? Now I can act with, no, sorry, the other way around, right? I want to produce something that takes a B, it takes an FB, right? So I F map this to give me FA, then P transforms FA to GC, and then I F map it with CD, so I get a GD, right? I mean, there's only one way of these things. This is called a type Tetris, right? If you make a mistake, it won't compile. If you do it right, it will compile, right? But you know, you just follow the lines, you know. So you just connect the dots, and this is the only way you can work with this, okay? So this is DIMAP for this guy. Now I can, since this is a bifunctor, okay, I can take an end of this, okay? So the end of NAT Pro FG, NAT Pro FG is a profunctor in A and B, right? In these A and B. I can take an end of it, right? And I call this type NAT. Why? Because these are natural transformations. This is what in category theory we call natural transformations between two functors. And if you plug in the definition, the for all definition, this is for all types x, a function from fx to gx, right? So this is what's called natural transformation. Well, in category theory, this would also require some diagrams to commute, right? However, in Haskell, these diagrams automatically commute. This is like the great thing about Haskell, that lots of diagrams commute because of theorems for free, right? Because of parametricity. So what this means that for any type x, if you have a container of x's, it will repack it into a container of x's using a different container. So it's like if you take a list, it will give you maybe, for instance, right? Stuff like this. So these are natural transformations. So in fact, you know, these things work. It is possible to define a profunctor that's non-trivial, right? And it's possible to define an end for it. Even though it looks like, wow, infinite product. How can you have an infinite product, okay? Now, in category theory, every time you have a construction like this, you automatically get one for free, which is the dual construction, which usually starts with the letter co. So if you have and, you can also define a co-and. And so what would a co-and be? I told you that this is an infinite product, right? What's the dual to product? Anybody knows what a dual to product is? Sum, right? Or coproduct or a sum type, right? So like the either thingy, right? A variant in other languages, right? So the dual to end would be sort of an infinite sum, right? So how do we write an infinite sum? This is how we write infinite sum, okay? Is this Haskell? No, not really, right? I'm cheating here. But exists means, I'll just translate it into Haskell in a moment, but this is a great note. I don't know why Haskell doesn't have existential types, because they can be encoded using universal types, but it would be nicer to have them in this form. Okay, so exists X, it means that if you want to construct a coend for the profunctor P, it's enough that you give me one of these guys for any type, you know, just pick a type, right? Integer, okay, good. Give me a P int int, and I have a coend, right? So they are easy to construct. Unlike ends, right, they're extremely difficult to construct. Coends are extremely easy to construct. However, you gain some, you lose some. They're extremely easy to deconstruct. Because if I give you a coend, then what do you do with it? You have no idea what type it is inside, right? That's the existential type. Well, there exists a type, but what? I don't know, right? But we'll see in a moment how you can actually deconstruct a coend. Even though you don't know what type it is, you can deconstruct it. Okay, so this is real Haskell, okay? This is actual Haskell. So the funny thing is, you know, every time you write something as existential, you can transform it into a universal type. How does this work? Well, what this says is that if you want to construct a coend, right, this is a constructor, coend here, right? This is my constructor, the name of the data constructor. This is the name of the type constructor, but this is the name of the data constructor. It means that you can call this guy, it's possible to call this guy with any type X, right? A data constructor is really like a function. I'm just saying this is a polymorphic function. You can call it with any type X, and it's fine, right? So as I said, you know, you want an int, fine, give me an P of int int. And you can construct this guy because it has a polymorphic constructor, okay? So an existential type is really defined using a polymorphic constructor. So notice that for all comes before the name of the constructor. That's the trick, okay? And it works. It works in Haskell. And this is the way of deconstructing. So what can you do with an existential type? You can call a function with an existential type, right? So let's see if you have a function that takes an existential type. What is it, right? So I'm saying, okay, so this is pseudo Haskell, right? This is a constructor C that takes an arbitrary X. So this is an existential type. And here's a function that takes this existential type and produces a Y. How is it implemented? Well, since X can be anything, this function has to be able to accept anything, okay? Therefore, it has to be a polymorphic function, right? So a polymorphic function is a function for all X. So whatever type X you give me, I can produce a Y. That's it, right? I have no idea what X is, but I don't have to, right? Because I can work with any type. A polymorphic type function can work with any type. So this is very important, and we'll be using this, okay? Because whenever we deal with existential types, we'll just say, okay, so we don't know what to do with an existential type. Let's just look at a function that takes an existential type and then do this conversion, and we are back to universal types, okay? Okay, and now we know what a profunctor is. It's like a functor that's contravariant in the first argument, covariant in the second argument. Now, I want you to completely switch your view and think of of a profunctor as defining a relation between types. Okay? So, profunctor of A and B. It says types A and B are related through this relation defined by this profunctor if PAB is non-empty. Okay? And if it's empty, it means these two types are unrelated. If they are related, then it's non-empty. But what does it mean non-empty, right? I mean, it could be non-empty in the sense that it has just one element, okay? Or could be non-empty because it's an int, right, which is infinitely many elements. Or it could be non-empty because this profunctor produces a function type, or, so, there are lots of possibilities. So the way to think of it is that if you want to prove that two types are in this relation, it's enough that you provide just one proof, okay? So every element of PAB serves as a proof, right? If I tell you, well, show me that this set is not empty, right? Well, how do you show it? Well, just give me an element, right? It's enough that you give me one element and you prove that it's non-empty, right? So every element of the set is a proof that the set is non-empty, okay? And I'm using set and type interchangeably. It's not really the same, right? But from the categorical point of view, like we can pretend that types are sets, okay? And I know mathematicians will know, yeah. I'm going to get really bad feedback for this, but okay. So you can think of these profunctors as proof-relevant relations. So now, why do I want you to think this way? Because I want to compose profunctors, okay? Like, how can you compose profunctors? A profunctor takes two into one, right? Two types into one type. So you cannot just compose it and pass this one type to another profunctor because it expects two types. So how do you compose them? Well, you compose them like relations. And how do you compose relations? Okay, so you say, I know that A is in relation with B, and I know that B is with relation in C. Oh, therefore, the composite relation is from A to C, right? And how do I prove that A is related to C? Well, as long as there exists the in-between guy, right? It's enough that I have one type that's in between these two. I have proven that they are in relation because I can bridge from A to B, from B to C, okay? So it's enough that there exists one B from which this is true, right? So if I can find the B, and now if these are proof-relevant relations, right, then it's enough that I have one element from this set and one element from this set, right? Maybe I should be drawing this stuff. I'm just drawing in the air. So one element from this set, like the fat arrow that contains many proofs, and one proof from this fat arrow, right? It's enough that I have a pair of these guys, right? And I have a proof, okay? So there must exist the set in the between, and there must exist a pair of proofs. Okay, so let's start with this point, right? So if I have two profunctors, P and Q, I want to construct a new profunctor from A to B, right? That is a composition of these two profunctors, right? So I'm saying there exists an X in between, right? So this is what the guy in between. And the proof of this relation that I'm constructing is a pair. So I have a pair of proofs. that A is related to X and X is related to B. Okay? A is related to X, X is related to B. Therefore, I'm saying A is related to B, and here's my proof, a pair. This pair is my proof. Okay? And of course, this translates into Haskell as, you know, this is an existential thing. If you want to translate it into Haskell, you have to use the universal type and the constructor of compose. Compose now is a type constructor. Well, this one is a data constructor. This is a type constructor, right? Because we are operating on types. Now, this is not functions. This is types, not values, types. Okay. So this is the definition of composition of profunctors. And now look what I'm doing. Okay. I'm just like moving you away from this one view to this other view in which profunctors sort of work like arrows between things, right? This is an arrow connecting A and X. This is an arrow connecting X with B. So suddenly profunctors appear in a different guise. They appear as arrows or maybe morphisms or something like that, right? Okay, so maybe there is a category sitting there, right? But hold this thought, because in order to prove that this is really composition, right, I need one more thing. I have to show that that what I'm getting is really a profunctor, right? So I just said I'm defining this data type compose using this formula, right? But is this a profunctor? Well, show me that it's a profunctor. How do I show that it's a profunctor? Well, if P is a profunctor and Q is a profunctor, then compose PQ is supposed to be a profunctor. Therefore, I have to define dimap for it. So dimap takes these two functions, con and pro, right, just like before, and takes a compose PAXQXB, right? So it takes a pair of these guys, these elements, PAX and QXB. Their type is this, but this is the name that I gave them, okay? And it turns out, well, then you can construct a new one by using dimap on PAX and using dimap on QXB, right? Because you want to like pre-compose one of them. You want to pre-compose PAB. So you use con, but you don't touch X at all. So the second function here is ID.
Excuse me?
Yes?
See when you are pointing from the left.
Or you could point from the right to the left and then.
Oh, because you're not seeing what I'm pointing at? Oh, okay, sorry. Okay, okay. So, and was it recorded on correctly? Yeah, okay. So, PAX, so PAX is a type, is a value from PAX, okay? This is a type, PAX. P acting on A and X produces a new type. This is an element of this type. QXB is an element of this type, right? So I have these two elements. Now I can apply dimap to PAX and I can apply dimap to QXB, right? So I'm lifting these two, and what am I lifting? I'm lifting two functions. One is this con function from here, right? But the other is ID, which means I'm moving A to A prime, and I'm not touching X. I don't want to touch X because X is in the between object, right? And here I'm moving B to B prime, but I'm not touching X. So I have ID here, right? So the X is untouched. This X is untouched. So I have the guy in between. Fine, right? And I'm just constructing this stuff. So this works. Now, this composition that I showed you can be written as a coend as well, okay? And to write it as a coend, I have to sort of like unglue the two variables. Maybe I should go backwards and show you what I'm ungluing. No, this is the end. Coend, right? So, no, not coend, a composition, right? Composition. Okay, composition, right? So, I want to unglue this x from this x. You see, this x. Okay. Oh, this x here, right? He is in the covariant position, right? Because P has a contravariant argument and a covariant argument. Here, x is in the contravariant position. This is the covariant argument to Q. This is the contravariant argument, right? So here it's covariant. Here it's contravariant. It's okay, right? But I want to unglue them. I want to say this is x and this is y for a moment, right? So I unglue them, and suddenly it becomes covariant in y, let's say, and contravariant in x. So it becomes a profunctor, right? And I call it a tensor product, okay? When I unglue two indices, sort of like, then I get sort of a tensor. So I have this, I have P and Q are profunctors, A and B are these external indices, and X and Y are the split X, right? And you see, this was X and this was X. But now this is Y. Okay, so I unglued them. And I can show you that this is a profunctor in X and Y. Okay? And this is, all, again, this is the type Tetris. There's only one way of doing this. So this is a dimap ID pro, dimap con ID. It just works. Okay? So this is indeed a profunctor, but now in X and Y. And because this is a profunctor in X and Y, then I can take a coend of this, right? And I can say that compose of PQ is a coend of this tensor product. So it's a tensor product. P is a profunctor, Q is a profunctor, A and B are these external indices, and the coend is taken over X and Y that are hidden here, right? So it's sort of like, you know, I mean, whoever, you know, if you studied physics, you know, it's like a tensor. You take a trace of a tensor. One is covariant, the other is contravariant. Take a trace, boom, you get this. So composition can be written as a coend of this tensor product. It's an interesting thing. Okay, now the Yone Dilemma. Anybody heard of Yone Dilemma? The Yone Dilemma? Okay, a few people. Okay, so I'm going to show you the Yone Dilemma in a kind of a little different way, right? It's actually what this is sometimes called the Ninja Yone Dilemma, right? By the people from Australia, the Australian school of category theory. It's a very strong school there. And they just came up with this name, Ninja Yoneda. Yeah? So it's a version of Yone Dilemma that starts with a profunctor, okay? So this is the Yoneda profunctor, okay? So, and I call it pre-Yoneda, because it's not yet Yoneda, but it's going to be a Yoneda. So you take a functor F. F is a functor, okay? A, X, Y are three types, okay? You think of A as a fixed type, okay? So this is a fixed type. And we are interested in the variation of X and Y, okay? So pre-Yoneda is, well, it's really a function type, right? This is a function type. It's a function that takes a function and produces a container of y's. Okay? Well, right. So if you want to remember this, right? This is, so there's a function from a to x. So you can see that this is probably, well, covariant in y. It has to be covariant in y because it occurs as a result of a function. But something that's on this side as the argument to a function will be contravariant. So, I mean, the intuition is anything on the right of the arrow is covariant, anything on the left of the arrow is contravariant, right? And even though there is another arrow here, this is on the right side of the arrow, so this is covariant. But it's contravariant with respect to this arrow, so, you know, like you count the number of arrows that you cross. Yeah? So this is indeed a profunctor, and blah, blah. Voila, it's a profunctor, right? Because I can define die-map for it. Right? So this is like a standard, yeah. Just look at it and becomes obvious, right? Pro-Yoneda here takes an argument that is a function from a to x and returns fy. So this is one argument, right? And it has to produce a function that takes a function from a to x prime, right? And what can you do with this function a to x prime? Well, you can precompose it with con, right? And then pass it to axfy. And then you can fmap it pro over it. Because the result of axfy is under the functor here. So you have to fmap, right? But other than that, it's just simple stuff. So what I want to do is I created this profunctor because I want to take an end of it. I really want x and y to be the same, right? But this is the same trick, you know. It's like I split this x into x and y, right? Now I do the end, and I get this, okay? So end of pro-Yoneda takes a functor f and some fixed type a, and it well, this is the definition of an end, right? I put for all x and do this, right? So the definition of end is for all x, the diagonal element, right? The diagonal element here of the profunctor. So the final result, I mean, this is all isomorphic, right? So the final result is Yoneda of fa is for all x, and I'm just plugging this in, so a function from a to x and fx. Now, this is the left-hand side of the Yone Dilemma. Yone Dilemma says, take all natural transformations, take all natural transformations from, and this is called the hom functor, okay? Because a hom set from a to x is the set of all functions from a to x, right? So this is the set of, so this type is a type from a to x, functions from a to x, and it's functorial in x, so it is a functor. This is why it's called a hom functor, because it produces a hom set. So hom functors are very important because there is always a natural transformation from a hom functor like this to any functor f. Okay? This is what Yoneda says. Now, in principle, you don't know. Does really a function like this exist? For any functor f, I can find a function like this? Yes. Yoneda says yes. And in fact, it says, this is the Yone Dilemma. This is the ninja Yone Dilemma, right? The ninja Yone Dilemma says the end of this profunctor, the end of this profunctor, which I call Yoneda fa, is isomorphic to fa. Now, if you think of it as a programmer, this just tells you that, okay, the container of A, I can express it as sort of using continuation passing. This is A to X is like my continuation, right? So this has something to do with the continuation passing transform, right? So Yoneda FA is this function that takes a function, it's a higher order function, but it's all isomorphic to just FA. So that's the beauty of the Yone Dilemma. And of course, once you have Yoneda, you have a, okay, this is the proof of Yone Dilemma in this language, okay? Just follow it very quickly. How do you prove stuff like this? Well, you have to prove that you have one-to-one correspondence. So you have to have a function from Yoneda to FA, right? From Yoneda to FA, and back from FA to Yoneda. So I just implemented these two functions. And this is really very trivial to implement them. This, again, there's only one possibility. You just call it with an identity, and here you fmap it. Just trivial stuff, right? Now, of course, you have to prove that they are inverse of each other, but that's also very, very simple. Right? So this is the Yone Dilemma. And there is a co-Yone Dilemma, obviously, right? But co-Yone Dilemma, this is the ninja co-Yone Dilemma. This is an interesting one, because actually it replaces stuff with a product here. So this is a pair, and it's an existential type, right? So I have a pair of a function from X to A, and I have a container of X's, okay? And I have no idea what X is. So when I'm constructing it, I pick an X, and I construct it. But if you give it to me, I have no idea what X you picked. So what's the only thing I can do with this pair? Huh? I can apply this function to X, right? But it's under a functor. Oh, but it's a functor, so I can fmap, okay? So the only thing you can do with this pair is fmap this function over this. And that's the encapsulation of the stuff. And if you fmap this function over this, guess what you get? You get f of A, right? So co-Yoneda is really equivalent to FA. Of course, you can. So this is a translation. This is an existential quantification. Like this is actual Haskell, right? This is the constructor co-Yoneda. Okay. And you prove it by showing these two functions back and forth. Again, what I said, right? You fmap xa over fx, right? That's the only thing you can do. Now, why did I have these Yonedas? Because we had this composition. I want to have a unit of composition. Okay, so here's our compose. This is how we were composing profunctors, right? So we take one profunctor, and it's an existential type, right? Takes one profunctor, another profunctor. This is this guy in the middle, right? So this is my compose. So what I want to show that this composition, the unit of this composition, is the hom functor, hom profunctor, right? I showed you in the very, very beginning an example of a profunctor. The simplest example of profunctor is just this arrow guy. He's a profunctor. It takes two types, one contravariant, one covariant. Okay? So I want to show that if I compose this profunctor with any other profunctor P, that I will get P back. Okay? So I rewrote it as, okay, so this is the composition in the existential way, right? So this is PAX, XB. So PAX is this P guy, and this is the arrow guy applied to X and B, right? X is the guy in the middle. It exists, right? This is this arrow applied to X and B. and this is P, okay? I can switch these elements. This is like flipping a pair. It's isomorphic, right? I'm flipping this, okay? And once I flip, I recognize that this is just a co-Yoneda, right? This guy is a co-Yoneda. The co-Yoneda, remember, was a home functor with a functor. Now, this is a funny functor. This is a functor in X, right? So I wrote it as P partially applied to A. It still has a room for an X, and it's covariant in X. So it is a functor. So it's a co-Yoneda in which a functor is PA, partially applied P, and B is this other type. And from co-Yone Dilemma, I know that this is this functor acting on B. PA acting on B, which is PAB. Okay? So I have proof that this arrow thingy is a right unit of composition. So if I compose on the right, I get back P, right? I have to show that this is a left unit of composition too, and I'm just going to skip it quickly, okay? I don't know if you can read this fast. you can slow down the video for the video people, okay? But this is the trick. There is a trick to it, okay? The trick is that I don't really know how to do this stuff to show the existential thingy. So I'm using the trick. I'm just looking at functions that take this thing and produce some C, an arbitrary C. So for all C, take a function from this guy to C, and at the end show that this actually produces a function from PAB to C. So if this guy, function to C, is equivalent to PAB, function to C, right? Then PAB must be equivalent to this guy. Now you might say, oh, okay, how do I know that? This actually follows from the Yone Dilemma again. You know, it's like if you have functions from a guy to an arbitrary object and they are equal, then the objects must be equal as well. Okay? So that's just the proof that it's a left unit. So it's both right unit and left unit of composition. So I can have a category now, right? But now I have several possibilities, okay? So it's like embarrassment of riches here. First of all, I can have a category in which objects are types and morphisms between them are profunctors, right? So this is this example in which morphisms are not just functions, they are profunctors. They are these relations that are proof-relevant relations, okay? It's a very interesting category, right? But I know how to compose them using these ends, right? And I showed you that there is an identity, right? So they actually form a category, right? In which profunctors are arrows. But I can also have a completely different category in which objects are profunctors, okay? Just like you have a category in which objects are types and morphisms are functions, you can have a category of functors between categories, right? In which functors are objects and natural transformations are morphisms, right? You can do the same with profunctors because profunctors are really functors from C op cross C, means a product of the opposite category and the category itself. Okay, the opposite category is the one which has all the morphisms reversed. So that's the contravariant part, right? So since these are just functors, then there are just natural transformations between them, right? So I can define a category in which profunctors are objects. So notice, here profunctors are objects, here they are arrows between objects, okay? So this duality, weird, right? And then we can combine these two views and say, well, profunctors actually form a monoidal category. So a monoidal category in which objects are profunctors, so we are just using this picture. Objects are profunctors. Morphisms are natural transformations between profunctors, so this picture. But there is this additional structure that we haven't used because we know that profunctors can be composed, right? From here, where profunctors were morphisms, right? So we have composition. We can say that composition of these profunctors, and now here are objects, it's sort of like a product. Because a product is when you take two objects and you create a third object, right? So since these objects are profunctors and they can be composed, and they can be composed nicely, right? Then I can say I have some kind of, and this is called a tensor product because it's not really categorical product. It's not a Cartesian product, of course, but it's a product in some way, in the sense that it's a bifunctor and so on, right? And this product has actually a unit, right? Which is this home profunctor, this arrow, this I showed you. So you have a category of profunctors that additionally has this monoidal structure where you can multiply objects thinking, okay, composition, right? And then there's a unit object thinking home functor, okay? So this is like two structures for the price of one. So now we are getting to arrows, finally. So since we have a monoidal category, we can define a monoid in this category. And this is where we started, right? We started with a category and monoid. So a monoid in the category of profunctors. So remember what a monoid was? A monoid was an object. We called it M, right? But here an object is a profunctor in this category, okay? So we'll call it P instead, right? And then we had this multiplication which was taking pairs of M and producing an M. Here, instead of taking a pair of M and M, it takes a product of P and P and produces a P, okay? So instead of using a Cartesian product or a categorical product, now we are using a tensor product, and it's still fine, okay? So we are using the tensor product, which we know on the back of our minds is that this is actually composition, profunctor composition, hello? This cross here means profunctor composition. And then there is the unit, right? And the unit was defined as the mapping of the unit object into, now instead of unit object, we can use the identity object, you know, the unit object in our monoidal category, right? So let me quickly translate this. Okay? So our mu is the tensor product going to P. The tensor product in our case was the composition. So compose P with P. P cross P. That means compose P with P and get a profunctor in AB, right? And it has to be mapped back to P, okay? So arrow PAB, okay? So we have to define something like this. If we want to define a monoid, we have to have this mu, okay? So what is this mu? Let's find what it composes. Composes, this exists X, PAX, PXB, right? Remember the common guy X going from A to B. This is the proof of the relation, right? But now we have a function that produces PAB. Okay, so this is a function from an existential type. Okay, we know a function from an existential type is a polymorphic function. So it's a for all x from this pair to PAB, right? Now I can curry this. A function of a pair is a function that produces a function. Okay. So after currying, I replace this with arrow, arrow, right? And I have this. So I have a polymorphic function of two arguments. Okay? And in fact, I can write it as an infix operator. This guy here, an infix operator. It's a polymorphic function from PAX and PXB to PAB. Okay? And anybody who's seen arrows will recognize this. Okay? This is part of the definition of the arrow. So we are getting closer, right? This is still called a pre-arrow. I'll show you in a moment why it's a pre-arrow. Okay? So this is one part of the monoid. One part of the monoid is multiplication. Now what about the unit? Okay, the unit is supposed to take this unit element with respect to my tensor product. And my tensor product is composition of profunctors. And the unit of composition of profunctors, well, that's a home profunctor, okay? Home profunctor acting on AB maps to P, okay, to PAB. And this is given a name R, like R, okay? Like a pirate saying R. Okay, so this is the second part of the definition of arrows, is this thing. Take a function and make it into an arrow. It's like a trivial arrow is a function, right? Okay. Now, this is pre-arrow because there's one more thing that we need. This is called a strength of a profunctor. So a strength of a strength is defined in this way, that if A is in relation with B, if you know that A is in relation with B, can you show me that if A is a part of some bigger product structure, right? It's like if you create these structures with lots of elements that, that have A as its component, is there a relation between these larger structures? If A and B is related, then are these larger structures related as well? And that's called the strength. So if you have strength, okay, then, and of course you have to assume, and this is something that you don't express in Haskell really, but you know, the laws, arrow laws are unit and multiplication of the monoid have to preserve strength. Okay, so this is an additional thing that you have to make sure. So arrows is a monoid in the category of strong profunctors. That's what it is, okay? So it's just like monad is a monoid in the category of endofunctors. Arrow is a monoid in the category of strong profunctors, right? So I'm just combining these things together so that to show you that the definition actually, this is from the library. The definition in the library says an arrow called R, right, has to have the following things. Has to have this. Oh, we recognize this is the monoidal unit, right? This is the identity object, and this is our R. This is the special profunctor that we are calling an arrow, right? First is the strength, right? Says, okay, it has to be a strong profunctor. R has to be a strong profunctor. And it has to form a category, okay? And the category part is this guy, okay? This triple arrow, right? That's defined as arrow, if R is an arrow, then RAB, RBC, RAC, okay? That was what we have defined. That was our monoidal multiplication, right? Or it was profunctor composition, right? And in fact, it's defined in the category as like the flipped dot operator, right? So it's enough to define the dot operator. Okay, and the final thing is give you an example of an arrow, okay? That's not completely trivial. So the non-completely trivial is the Kleisli arrow. The Kleisli arrow, for every monad M, right? So M is a monad. You can define this thing, which is a profunctor. It's contravariant in A and covariant in B. So these are functions from A to MB. Okay, so these are the functions that return the embellished results, monadically embellished results. And we know that these Kleisli arrows, for a monad, they are composable. And the composition for these Kleisli arrows is this fish operator, right? So here's the proof that Kleisli arrows are actually arrows, okay? So the monoidal unit, okay, you take a function from A to B, and you embellish it. How do you embellish this function? Well, you follow it with return. Return just lifts it to a monad, right? So a function from A to B followed by return will give you a function from A to MB, okay? And first, well, you just pattern match this pair, right? And then you apply f to the first element of the pair, and then you reconstruct the pair. It's a typical so Kleisli arrow is actually a strong arrow, and it forms a category because it has identity. Well, the identity is just R, right? Acting on ID. And the composition is just the fish operator. Okay? So this is a simple example of, after all this complex stuff, this seems simple, right? Okay? So a Kleisli arrow is actually an arrow, yeah. And it forms a category, and it has strength and all this stuff, and monoidal unit and composition and so on. So to conclude, right, what have we done? We were juggling categories like crazy, right? So we have morphisms in one category, these profunctors, right? But they are objects in another category, in the category of profunctors, right? And we were combining these disparate structures, you know. We created a monoidal category that combines a monoid with a category, right? Inside this monoidal category, we defined a monoid, right? And that was our arrow. Okay, so it's like, I mean, you can learn it from the Haskell library, but really you don't understand it until you get the categorical view of this. I think this is like this is the power of category theory here. Okay, thank you. Any questions?
I have probably the easiest questions.
Okay.
So, like, monads are monoids in the category of endofunctors, arrows are monoids in like this higher dimension category of functors. If you go like higher dimensions, so to speak, is it something interesting as well?
I think here the trick is that you know that when you have functors that take two arguments, right, then they can be viewed in different ways, right? A functor of two arguments can be seen as defining a product, right? Or it could be seen as defining a morphism in this case, right? Now, I don't know, are you thinking of functors of more than two arguments? Yeah, I don't know. So this is sort of like saying, you know, once you have functions of one argument, Then you have functions of all arguments because of currying, right? So probably these are like the basic blocks that you can think of, right? Everything else can be obtained by partial application. So, I mean, you can combine these structures in various ways, but I don't know if there is anything. Yeah.
What I meant is that like monad has different constraints on the elements and arrows.
Mm-hmm.
The constraints or the arrows are stronger in a sense than for a monad, and accepts one more argument. So, so what I was thinking is maybe if you accept another argument, the constraints change again. Maybe this is.
I don't know. I haven't heard of anything like this. So this is really a difficult question. It's not an easy question. Let me quickly come up with an idea. Right? Super arrow. I don't know. Okay. Anything else?
I think I missed why you need strong for an arrow.
Well, I cannot explain why you need strong, okay? It just happens that for programming purposes, strong is good, okay? But in general, you know, I mean, you have data structures that are either algebraic data structures are either products or sums, right? So this just tells you that this sort of is composable within data structures. So if you have a data structure that's a product, you know, like you have a record, right? You have lots of stuff, and you know that there is a profunctor connecting an arrow connecting these other, these one component of this big thing, right? That you can sort of carry the rest of the baggage without changing it. So from programming point of view, this is great because you know you have this huge thing and you say, well, I'm applying arrow to only this thing and I'm not touching this. What does it mean I'm not touching this, okay? This means not touching this. This means strength, okay? It means you can move this whole thing without touching the rest. And this is like the idea behind lenses, right? Is the same, you know, so you have a huge product and you're just saying, I'm focusing on this little thingy and I'm moving it here, right?
So that's what strong gives.
Yes, yes. Yeah, first is just means like, you know, if you can do this for a pair, then of course you can easily do it for any product, right? So a pair is just a simple example. It's enough to show it for a pair, and then you can generalize it, and you can get, you know, like arbitrary product type, and you get it. Yeah.
Back in the pre-arrow slide, there was a you said that the unit is equivalent to a function when proving the monoid category. And I didn't understand that. It was a category of strong profunctors. You were showing in that
Pre-arrow.
Yeah, pre-arrow.
This, the last one.
Yeah. So. How come the function is equivalent to the units? It doesn't mean that there isn't one element in the set.
Okay, so this is the way of defining a monoid in a monoidal category. Okay, so in a monoidal category, you have a product and you have this unit. Okay, unit object.
Yeah.
And this is a unit object with respect to this product. So this product was a composition of profunctors. This is a symbol, you know, like inside of the symbol we see that this is a composition of profunctors. Then what is the unit of composition of profunctors? It's the home profunctor. That's what the Yone lemma was showing, the Ninja Yone Dilemma shows that it's a home profunctor is the unit of composition. So, okay, I know this is like juggling again. So you have a category in which these profunctors are objects, right? And there's one particular profunctor sitting here that's the unit, okay?
So maybe I can rephrase my question.
Okay.
Because at the beginning you showed the equivalent definition of a monoid, and the empty value was defined instead as a function from unit, which is a function from a set of one element. So this is equivalent to just a value, right?
Right.
Not here. It doesn't seem like this is the case. It's now it's a function from a function to something. And that's why I'm confused.
Okay. Okay, so this is one of these typical categorical generalizations. When you start with something that obviously is, yeah, like, oh yeah, it's a one element set, so obviously a morphism from this one element set is picks an element, right? But then you say, okay, but what if I don't know what a one element set is? Well, okay, well, maybe you have a terminal object. Terminal object doesn't have to be, you know, in a set, in the category of sets, it's just a one element set, so that's fine. But in a general category, it's not, okay? It could be something different. But you're saying, I'm going to close my eyes and say, pretend that it's, you know, let's see if it works, right? It's more or less says, let's see if it works, right? So now you generalize it and say, okay, well, I don't even have a terminal object. I just have this unit that's sitting around. What if I generalize the definition of a monoid to an arbitrary monoidal category in which I don't have a single element set. I don't have a terminal object. Maybe I do, but you know, I don't care. But I have this unit here, okay? And like, what is important about this thing that it's a one element set? Maybe it's not really important that it has a one element. Maybe what is important really is that when I take the product, this tensor product with this element, that I get that it's a unit of this stuff. And it worked with pairs, right? When you take a pair and put unit as the first element, then it's equivalent to the second element of the pair. It's like one-to-one correspondence, right? So maybe this is important. Maybe it's not important it's a one element set, right? I mean, we start with something that we understand, and then we say, but what if we just like use something different? Which property of this one element set was important, right? To our understanding, in the beginning, it was important that it picks an element, right? But now we are saying, well, maybe that's not important. Maybe it's important that this special element, the special type or the special object in the category that is special by being a unit of this tensor product. That's the special thing. Aha, that was the special thing. Forget about one element set, right? I know, I mean, you lose this intuition of a one element set at this point. And you say, but so what? You know? It works, then it's fine. As long as it works, it's okay. I mean, in category theory, it's always asking this question, what is the important property of the thing that I'm using? Is it important that it's a number? Is it important that it's a set? Is it important that it has this property or that other property? Like, what is the property that I really, really strongly need? And in this case, it turns out that the property that you really, really need is that this is a unit of this multiplication. And it doesn't even have to be a strict unit. Like in the case of pairs, it was up to isomorphism, right? It wasn't even strictly unit. It was like a lax unit, relaxed unit, right? It wasn't even strict unit. So you just like relax these things and say, I don't care about that, I don't care about that. I mean, the power of abstraction is being able to say, I don't care, right? Like, I don't care that this is a set. I don't care that this is a number. There's this one property that I think is important, and everything else, I'm just tossing it. Abstraction means subtracting stuff, right? Tossing it, saying, I don't care. And it's like the knowledge what can be tossed and what cannot makes all the difference. Okay? So that's not really an explanation, but hand waving, right? Yeah. Anything else?
So I think the meetup title was actually included free in there. Am I wrong? Was it not? That's.
Yeah, I don't know.
Did I? I don't think I. Is it a free Pro Functor?
The arrows are strong free profunctors.
Did they say free? Yeah. Ooh. Well, okay, so the meaning of this is I'm not charging you for it, okay?